This call is now being recorded.
Welcome to lecture 4, Aksharamaala physics class. I'm Priyansh. I'll be continuing the things which I left in last class from where. That is the Bose and Bury rule. So far we saw how electrons are arranged in an atom in different shells, or you can say different orbitals. This we studied in last class, and this was defined by the Bohr and Bury scheme, for which we did some examples also. So today we will continue from here and we'll see why molecules are formed. As a primary question, and some other topics also. So for this we study valency. Before that, there is a term called valence electrons. What is valence electrons? These are the electrons present in the outermost shell or orbits. This is not orbital, this is orbits. Electrons present in the outermost shell or orbits of an atom, of an element. Like for example, let's take an example of lithium. Lithium has nucleus at the center, 2 electrons in the first shell, that is K shell, and 1 electron in the L shell. So number of electrons in the outermost shell, that is L shell, is equal to 1. So lithium has 1 valence electron. Similarly for other elements, and we'll see for other elements in upcoming discussion. Also from Bohr-Bury discussion, or you can say Bohr-Bury scheme, we conclude that from one of the rules, it says that maximum number of valence electrons, that is electrons in the outermost shell, is equal to 8. It cannot exceed 8. So this is another condition for valence electrons. You can say that the maximum number of these can be 8. And observations from nature have been made by the scientists, and it shows that atoms of some elements that have completely filled 8 electrons, or you can say completely filled shell, that is they have 8 valence electrons, are very stable. By stability, what does it mean? That it means that they show very less chemical activity. And by chemical activity, it means that they rarely form any molecules with other atoms. And there is an exception also, like the number of valence electrons has to be 8. But for helium, there are only 2 electrons, right? And they are both in the K shell. So for helium, the outermost shell is still completely filled, but number of valence electrons is 2. So this is also stable, but the number of electrons are not it, because the K shell can only hold 2 electrons and helium also has 2 electrons. So K is full and uh, number of valence electrons are also maximum. So these such molecules which have completely filled outer shells do not form any molecular bonds with other atoms. That is, they show less chemical activity or are very stable. This is observation which can be made in laboratories. So now let's look into the definition of the valency. Valency is defined as, you can say, for an element, it is the measure of its combining capacity with other atoms of some element to form chemical compounds, or you can say simply molecules. So what does it mean is that, suppose there is a hydrogen atom, it has one nucleus and one electron, right? So there can be some other element, say, for now say X element, it has a nucleus and it has some number of electrons which we don't know. So the sense here is that the valency for an element is the combining capacity. It is the measure of combining capacity. So the valency number, which will be for hydrogen, will tell us how strongly it is allowed, or it wants to make a bond with another atom to form a chemical molecule or a chemical compound. So it defines the combining capacity. So for the fully filled shells, the fully filled outermost shells, which have 2 electrons for K shell and 8 electrons for other shells, like helium, which has 2 electrons at outermost shell, and say neon, which has 8 electrons in outermost shell, 2 in K and 8 in L. These show least chemical activity because they are fully filled. So in other words, you can say that their valency, that is the measure of combining capacity with other atoms, is 0. So this is how we define valency. So this was proposed that valency explains why molecules are formed. Since we just saw that valency means the combining capacity of any atom to combine it with the other atom in order to form complex molecules or some simple molecules, they came up with an idea to define, like, valency explains why molecules are formed. So this combining capacity and quickly write it. It can be asked as a question. Or just for your understanding, also, you should know why we look into the valency, like why is it important. So, the combining capacity of the atoms of elements, that is basically tendency to react and form molecules excuse me, with atoms of same or elements. The combining capacity of the atoms of elements is the tendency to react and form molecules with atoms of same or different elements as an attempt to attain a fully filled outermost shell. So this is the reason why molecules are formed. That is, for example, what does this statement mean is that, say, for helium, there are two electrons in the K shell. So it is already stable and has very less chemical activity. It does not form any compound. It hardly form any complex compounds. But say sodium. Sodium has 11 electrons. So 2 goes in K shell and 8 in L and 1 electron in M shell. It has one more electron from being completely filled outermost shell. So, in order to attain stability, it will form a bond with some other atom, or say it can form some bond with its own element, that is sodium, but that won't lead it to stability. So, usually, what happens is sodium with one electron in M shell combines with chlorine, which has 7 electrons. It is the atomic number for chlorine is 17, so it is 2 in K, L, 10, and 7 in. Oh, again. 7 in M shell. So they share a bond, and this uh, electron, it is thrown towards, you can say for now, towards the chlorine, and it contains now 8 electrons, and the sodium has now 10 electrons. Although it does not, mm, yeah, it's actually transferred completely because it's an ionic bond also. And after attaining one electron from sodium, chlorine has now 19, sorry, 18 electrons. That is 8 electrons in the outermost shell, but still the protons are 17, which are inside the nucleus. So it retains stability and one negative charge. And for sodium, this one electron, this goes here. It becomes 8. So it has now only 10 electrons in its outermost shell, which is L. It is now completely filled, and M shell for chlorine is completely filled. So they attain stability. So this valency explains, the combining capacity explains why this bond is formed. So this is simply written here, the attempt to attain a fully filled outermost shell. Excuse me. There is some terminology also related to this. An outermost shell or orbit possessing 8 electrons in total is said to possess an octet. Oct basically is the prefix for 8. So, like here in Na positive, there are 2 electrons in K shell and 8 electrons in L shell. The L shell is said to possess an octet. Octet means like it possesses 8 electrons. So this was about octet. So this valency tells us that the atoms would thus react as so in order to achieve an octet in the outermost shell. And this achievement of octet is done by either sharing, losing, or gaining electrons. Like the example which I just gave is of the NaCl. It is an ionic bond. You don't have to worry about the ionic bond itself for now. Just look at the number of electrons. So here, sodium passes its 1 electron to the chlorine. So sodium loses 1 electron to attain stability, and chlorine gains 1 electron to attain stability. And there can be some instances where the electrons are not completely transferred, or the atoms do not lose or gain any electrons, but they share it with some other element. So they both mutually have completely filled shell, we can say. For example, in hydrogen gas, hydrogen has one nucleus in which there is one proton and one electron. So the outermost shell, the K shell, does not have fully filled electrons, that is the its capacity, which is 2. But there is another hydrogen which has one proton and one electron. So neither of them can just transfer it because it is the only electron they have. So they form something called which is called as covalent bond, and they both share the electrons. This electron will be shared with this nucleus, and this electron with this nucleus. So now they both have 2 electrons, but they are not solely for the one atom. It is a kind of joint agreement, you can say. So they attain stability by sharing electrons. So these can be 3 instances: sharing, losing, and gaining. Excuse me. Now, for an example, what is the valency of magnesium and aluminium? Suppose a question is asked like this. So, how will we calculate it? So, valency is now basically the number of electrons in the outermost shell. Just let me put a table also. So, valency is the either number of electrons in the outermost shell or there is one more case, number of electrons in the outermost shell. So like here, for example, you can say for hydrogen there is 1 electron, so valency is 1. For helium there are 2 electrons in the K shell, which is the capacity. So this is least active regarding chemical interaction. So the valency is 0 for this because it is already stable in itself. Similarly, for lithium, there are 3 electrons. 2 are in K shell, 1 is in L shell. So valency is 1. Similarly, for other atoms. But if the number of valence electrons in the outermost shell they exceed the number 4, that is half of 8, then the valency can be either defined by the number of electrons it possesses or the number of electrons it needs to become 8. That is, take the example of this, say first let's take the example of oxygen. So oxygen has 8 electrons, 2 in K shell and 6 in L shell. So it has 6 electrons in the outermost shell, that is L shell. But it is easier for it, rather than losing 6 electrons, it is easier for it to gain 2 electrons or share 2 electrons with some other atom. So its valency is not 6, but it will be 8 minus number of electrons in the outermost shell, that is the number of valence electrons, which becomes as 2, that is 8 minus 6 is equal to 2. And in some cases, like say phosphorus, it has 5 valence electrons, that is there are 5 electrons in the outermost shell, that is M shell here. So it can either lose 5 electrons or lose 5 electron or gain 3 electron. And it is observed that it makes the bonds in both of the ways, either, or it can share also. So its valency is considered to be both. So there can be some cases where the uh, atom of an element might have more than one valency depending upon in which compound it is. Like in HCl, this is phosphorus, right? Chlorine has gained one electron. So say NaCl, it has gained one electron. So its valency is 1 here. So we were on this example, magnesium and aluminium. So for magnesium, we have Z is equal to 12. It has 12 electrons. So we will apply Bose-Bury rule, 2, 8, and 2. So the number of valence electrons is 2, which is in the outermost shell, M shell. Since 2 is less than 4, that is the half of 8, which is the maximum capacity, its valency is 2. Similarly for aluminium, it has 13 electrons. So configuration will be 2, 8, and 3. So valency is equal to 3. Now let's take some more example. It is an NCRT question. How will you find the valency of chlorine, sulfur, and magnesium? Magnesium we just found, it is 2. For chlorine, let's see. It has 17 electrons. Alright. So according to Bose-Bury rule, the configuration will be 2, 8, and 7. So since the number of valence electrons is 7, that is greater than 4, its valency will be 8 minus NV. That is 8 minus 7 is equal to 1. So magnesium is in chlorine is done, and sulfur. Sulfur has 16 electrons. So its configuration is 2, 8, and 6. 6 is greater than 4, that is half of 8. So 6 is the number of valence electrons. So valency will be 8 minus NV, that is 8 minus 6, that is 2. So for sulfur also the valency has been calculated. So this was all about valency. One second. Now we will look into atomic number and mass number. There might be some noise in the background. Just ignore that, I can't control it. I am writing solution. So, what is atomic number and what is mass number? By definition, the atomic number is the number of protons inside a nucleus of an atom of an element. And by fact, all not atoms, all elements are defined by this quantity itself, that is the atomic number. Like if you are given two elements, two atoms of two different elements x and y, so how would you define them? We will just calculate the number of protons it has. Suppose it has 8 number of protons, so it will be oxygen. If it has 7 number of protons, then it will be nitrogen. So the atomic number itself defines the elements, and it is denoted by Z. And if you take two atoms of a given element, say I give you two atoms of lithium, one atom is this and one another atom is this, they both will have same atomic number, that is Z equal to 3. So all the atoms of a given element or of a certain or a particular element have same number of protons. Like for, let's calculate some examples for hydrogen. Hydrogen, inside nucleus there is one proton. Outside there are electrons. We are not interested in that. We are just interested in protons. Because electrons can be shared also, or it can rip off of the atom also. So that is not very reliable. Protons are inside nucleus and they are hard to take out. So it has one proton. So its atomic number is Z. That is why it is the first element in the periodic table also. For carbon, say carbon has 6 protons and its mass number is 12. So there are 6 number of protons and 12 minus 6, that is mass number minus number of protons, is equal to number of neutrons. So Z is equal to 6 for carbon, that is 6 protons. Now what is mass number? Mass number is before mass number, the mass itself. The physical mass is practically due to two subatomic particles, that is neutrons and protons. We saw in earlier class that These two are solely responsible for the mass of atom because electrons are very light as compared to protons and neutrons, and they do not provide any significant contribution in the mass. So all the mass comes from neutrons and protons itself. And mass number is nothing but total number of protons and neutrons in an atom, and it is denoted by A, number of protons plus number of neutrons. And these neutrons and protons, we saw earlier that they both inside the nucleus. Hence, they have a collective name also. The neutrons and protons residing inside the nucleus, they both together are known as nucleons, derived from the word nucleus itself, I think. For example, let's take the case of carbon. Carbon has Z equal to 6, that is the atomic number, and its mass number is 12. So Z also tells us that the number of protons is 6. So it will practically have A minus Z number of neutrons. That is 12 minus 6. So it has 6 neutrons. If we are not given with the mass number and we know the number of protons and number of neutrons, we can just add these two and it will give us the mass number of the atom. And since each of these nucleons weigh up to 1 U, that is 1 unified mass, the total mass will be A and there will be alphabet U. That is for carbon, its mass is atomic mass is 12 U, 12 units, you can say. So this was all about atomic number and mass number. And now from these definitions, some categories comes under which some elements are defined. First is isotope, and second is isobar. There is a third also called isotones, but we will focus on these two only for now. Isotopes are the elements which have same number of protons, that is the atomic number, but have different mass number. Like the element, say hydrogen. If you pick an atom of this element, so it has been observed that sometimes its mass comes out to be different. Usually the mass of hydrogen is taken as to be 1 U. But sometimes if we take some atom of the hydrogen element from the nature, it mass will come out to be 2 or 3 also. So such elements which have same but still being the mass being different, they still have one proton inside them. So such element which have same atomic number, that is same number of protons but different mass number, are called isotopes. Just like the example I said, for hydrogen we have 3 isotopes, that is 1H1 which is called protium. That is one proton, which gives its mass equal to 1 U. Then there is another one called deuterium, 1H2. Its mass is 2U, but still there is one proton inside it, and the other mass, that is 1, it comes due to there is one neutron also present inside the nucleus. So it will be one proton and one neutron inside the nucleus. Then there is one electron. For this one, that is protium, there will only be one proton and one electron. Third one is tritium. Its symbol is 1H3. It has one proton again because Z is equal to 1 for all of these. Only thing is the neutrons, the number of neutrons inside the nucleus are varying. It has this A minus Z, that is 1, is equal to 2 neutrons. So such atoms, you can say, of the elements are termed as isotopes. So protium, deuterium and tritium are isotopes of hydrogen. There are other examples also for carbon. We have 6C12, that is 6 protons and 6 neutrons, so giving mass of 12. There is also 6C13 and 6C14. This one has one additional neutron and this one has two additional neutrons as compared to the 6C12. These are isotopes of carbon. And similarly, chlorine also have isotopes, 17Cl35 and 17Cl37. That is, they both have 17 protons, but number of neutrons vary by 2 in this one. So isotopes are atoms of same elements having same number of protons or same atomic number and different mass number. That is different number of neutrons. The other is isobars. Isobars are the atoms of same elements. Isobars are the atoms of different elements having same mass number. Let me write it. Atoms of different elements having same mass number. Since we have said that it is the atom of different elements, it directly implies that the Z for the two isobars will not be equal, but their mass number will be equal. For an example, take an example of argon and calcium. They both are atoms of different elements. One is from argon and one is of calcium. This one has number of protons, that is atomic number as 18. This one has atomic number as 20, but both have mass number as 40. Such species are called isobars. It is due to the number of neutrons. This one has 22 neutrons and this one has 20 neutrons. So they both end up having same mass number. And isotopes, I can tell you the definition. Isotopes were same number of protons. Isobars, same mass number. Isotones are something which the species of elements which have same number of neutrons. That much will be enough for class 10th level. Now what's next? Okay, so many elements, like just we saw, have different isotopes. So many elements, these are not found purely in nature. These are found as mixture of isotopes, mixture of their isotopes. But each isotope in itself is a pure substance. Suppose I capture some carbon gas, not oxygen. Let's take example of chlorine itself. One second. Okay, never mind. Take example of chlorine. If I capture some chlorine element, then not all the atoms of the elements will have mass number as 35. Some of the atoms will have mass number 37. So any element in the nature is found as a mixture of its isotopes. And each isotope have same chemical properties. But different physical properties. Why is it so? Because isotope have same number of protons and naturally they would have same number of electrons also. And chemical properties are usually defined by the number of electrons in the outermost shell. So they have same chemical properties. But physical properties like mass is defined by the number of protons and neutrons. So for isotopes, different isotopes of same element, they will have different mass number. Just we discussed for chlorine, 17Cl35 and 17Cl37. So these two isotopes will have same chemical properties, but their physical properties like mass will vary. So the mass number has to be defined or replaced by average atomic mass, because there is not one pure substance of chlorine, and in nature the ratio of these two elements is found to be 3:1. That is, suppose for an example, if I capture some chlorine element and there are four chlorine atoms inside the container, so there is a highly likely chance that three of them will be 17Cl35 and one will be 17Cl37. Not always, but most of the time. And suppose I capture 40 atoms of Cl, then 30 will be Cl35 and 10 will be Cl37. That is the meaning of 3:1 ratio. Now there is something called average atomic mass, which is defined depending upon this ratio. It is defined as the percentage of first isotope into atomic mass. Just let's write A. The system is lagging somehow. Let me quickly restart it. Hmm. Average atomic mass will be defined as summation of percentage of ith isotope multiplied by atomic mass of ith isotope. For example, what does it mean is that, for example, let's take the example of chlorine. For chlorine, we have 3:1 ratio for 17C35 and 17C37. So average atomic mass for chlorine will be 3 ratio means 75%. So 75 percentage of ith isotope and its mass number, that is 35 plus 25%, that is 3:1 ratio. If you divide 75 by 25, you will get 3 by 1. 25% of 37. So this will give you out, I've already calculated, it will see 25% of 37 and 75% of 35. When added, it will give 35.5 U. It's not mentioned in this table. Anyways, when you solve the problems, most of the times, like mostly always, the mass of chlorine is given as to be 35.5, because the other isotope has considerable amount of percentage in the nature, that is 25%. But hydrogen will always, the mass of hydrogen is always taken as to be 1 unit until its isotope is specified, because the other isotopes have very small percentage as compared to the protium, so such that they does not add much to 1 U. But for chlorine, the percentage is quite high, so its average atomic mass has to be taken. But this average atomic mass, it does not mean itself. It does not mean that mass number of chlorine is 35.5. It's just that if we take some amount of chlorine element, then the average mass of the atom will come out to be 35.5 U, not of a single atom. These isotopes have some applications also, although their chemical properties are same, but some special physical properties they possess. Uh, some example are isotope of uranium. It is used as fuel in nuclear reactor. An isotope of cobalt. It is used for treatment of cancer. This question can be asked in your exams also. Applications of isotopes. So should remember it, maybe. Depends on you. Then there is isotope of iodine, which is used for treatment of a medical condition. Excuse me. Treatment of a medical condition called goiter. Now let's solve some questions. If question 1 is, if number of electrons in an atom is 8, this is given to us. Number of protons is also 8. Then what is the atomic number of the atom? First part. Atomic number is same as the number of protons, so Z is equal to 8. What is the charge on the atom? Number of electrons is 8, so 8 minus, and number of protons is 8, so 8 plus. Total charge when added, minus 8 plus 8 cancel out, and total charge is equal to 0. Q is equal to 0. Atom is neutral. Next question. With the help of table 4.1, find the mass number of oxygen and sulfur atom. So table 4.1 is this one. Mass number of oxygen. Excuse me. Oxygen has 8 protons and 8 number of neutrons. This is atomic number. So its mass number will be 16. 8 plus 8 equal to 16. For sulfur, it has 16 protons and 16 neutrons. So its mass will be 32. Mass number is equal to number of protons plus number of neutrons. It's again stuck. Let's restart it. And this is the symbol when we write an element. Suppose I write 6C12. So the the alphabet appearing here represents the element itself. C is for carbon, and each element in the periodic table have a different alphabet. Hydrogen has H, helium has He, oxygen has O. This number at the lower left bottom, it is the atomic number, that is 6 number of protons, and appearing at the upper left is the mass number, that is 12. Is it stuck again? Excuse me for this technical issue. Oops. For H, D, and T, tabulate 3 subatomic particles found in each of them. H, D, and T are basically the isotopes of hydrogen. H is protium, so 1H1. D is deuterium, 1H2, and T is tritium. This one is right like this: proton, neutron, and electron. One proton, one electron, because Z is equal to 1. Mass number is 1, given by proton, so number of neutrons 0. One proton, one electron, same for tritium also. The difference in number of neutrons. Isotopes have same number of protons, so you can directly write 1, 1, 1. Number of neutrons will be A minus Z, that is 1 minus 1, 0, 2 minus 1, 1, 3 minus 1, 2. That solves first question. Write the electronic configuration of any pair of isotopes and isobar. So let's do for hydrogen only. Or maybe we can do for chlorine. 17Cl35, 17Cl37. What will be the electronic configuration? 2 in K shell, 8 in L shell, 2 at 10, 7 in M shell, 17. Now, what will be the configuration for isotope of chlorine, that is 17Cl37? It has same number of electrons, so same configuration. Isobar. Isobars will have same mass number. Example, argon and calcium. Its electronic configuration will be KLM288, which gives 18 electrons. For calcium, it will be 288, and instead of other two electrons going into the M shell, because it has maximum capacity of 18, but Bohr's rule has to be applied, and the outermost shell cannot have more than 8 electrons. So the 2 electrons will go to N. So this is the electronic configuration for isotopes and isobars. This is a pair of isotope. This is a pair of isobar. These are some other questions. This is theory question. Na positive has completely filled K shell and L shells. Explain. So this we also discussed, because Na loses one electron, it becomes Na positive, that is 10 electrons, 2 in K and 8 in L shells. That is the explanation. If bromine atom is available, say 2 isotopes, this much percentage, calculate the average atomic. It's same as we calculated for the chlorine, 49.7% of this one, that is 79, plus 50.3% of 81, that is this atomic mass. So this will give the average atomic mass of bromine. You can calculate it. The average atomic mass of a sample of an X element is 16.2 U. What are the percentages of the isotope in the sample? Yeah, this question is good. It says that average atomic mass of an element is X. Of an element X is 16.2 U, and its isotopes are 8x16 and 8x18. So what is the percentage of these? It is easy to calculate. You can suppose this isotope with 16 mass is m%, and the other one will be, say, n%. So total percentage should be 100. So this one will be 100 minus m%. So we have m% into 16 plus 100 minus m% into 18 is equal to, given us 16.2 U. So m% is 0.01 of m into 16. M% is basically m by 100 plus 100 minus m. So it becomes 1 minus 0.01 m multiplied by 18 is equal to 16.2. This becomes 0.16 m plus 18 minus 0.18 m is equal to 16.2. This becomes minus 0.m is equal to minus 1.8. So m becomes 1.8 upon 0.02. This becomes 180 by 2, becomes 90. So m is 90, and m was the percentage of 8x16 and 8x18. So m% is 90% of this first isotope, and 100 minus m%, that is 100 minus 90, is equal to 10% of the second isotope. If Z is equal to 3, what would be the valency of the element? Also name the element. If Z is equal to 3, then electronic configuration is 2 goes in K shell, 1 is in L shell. It is less than 4, so number of electrons, that is number of valence electrons, is itself valency. And it is lithium, which has 3. Z is equal to 3, right? So it is 3Li7, that is lithium. Composition of the nuclei of two atomic species X and Y are given under S. X has 6 protons, 6 neutrons. Y has 6 protons, 8 neutrons. Give the mass number of X and Y, and what is the relation between the two species? So mass number for X is 6 plus 6, that is 12. Mass number for Y is 6 plus 8, that is 14. This gives us the mass numbers. What is the relation? We see that number of protons is same, but mass number varies. So such species are known as isotopes. This question is also complete. I'll soon float an assignment also. Although I've posted one assignment also. Where is it? This one. Assignment number 1. And the deadline, oh, it logged me out. No, never mind. The deadline for it is, I think, 2nd of January. That is 1 week from the date of when the assignment was posted. Soon I'll post another assignment, and it has only one question, so there is not much burden of it. You can solve it easily also. The thing was covered in class. From there only I give the question. If you have any doubts regarding assignment also, you can just ask me directly in the WhatsApp group or the platform on the Aksharamaala itself. So let's conclude our class. And this concludes the 4th chapter also, the structure of atom. Structure of the atom. Thanks for watching.